Hey guys, welcome to the first set of notes for chapter 16. We're continuing acid and bases with acid-base equilibria. It's a little more work with ice charts. We're going to get you up to about titrations today, and hopefully you find it reasonably interesting and something that's workable. So let's talk about acids and bases. The common ion effect is the first thing we're going to talk about. It's really just an application of Le Chatelier's principle from earlier in the year. It's a shift in equilibrium caused by the addition of a compound that has an ion in common with a dissolved substance. So the presence of a common ion suppresses the ionization of a weak acid or a weak base, which again sort of makes sense. So here we can say we have a strong electrolyte, CH3COO with sodium on the end, and then our acetic acid. And when this is a strong electrolyte, it'll break apart into sodium plus ions and then CH3COO minus ions. And the CH3COO minus ions would be like adding, more product to the right, shifts equilibrium to the left. And so that's suppressing that ionization of that weak acid. So that's kind of how that works. And so here's your equation. This ion, or rather this strong electrolyte breaking apart into its individual ions, and then applying that ion there. I think it's an acetate ion, I could be wrong. Applying that acetate ion concentration into this equation will actually shift our equilibrium back to the left, over here to our acetic acid. And so really we're just kind of building on last chapter's acid-base equilibria and the ice charts that we've done before to work with two or more, acids or bases or salts together. So it's just kind of one step further into understanding what's really going on in a beaker of acids and salts. So that would be the common ion, of course, because it's present in both of our equations. And then shifting left, which we just explained. So what if we mix the salt Na and the weak acid Ha? We can say that Na, the salt, breaks into the ion of sodium and the ion of A minus, whatever that acid might be. And then Ha breaks into hydrogen plus and then A minus. Now we have a common ion here. So when we look at our Ka is only concerning our acid-base reaction. It doesn't concern the salt, of course, because the salt is not a reversible reaction. So there's no equilibrium constant for it. The solid wouldn't be written at any rate, but because it's a one-way reaction, we only worry about our acid and base because those are a reversible reaction. So you can rearrange that to solve for your hydrogen ion concentrations, and then from that we can derive this equation, which has some really long name like Hasselbalch or something like that. Henderson-Hasselbalch equation or something. But it is pretty useful, actually. It's the pH is equal to the pKa, which is just the negative log of the Ka. And the Ka you can look up in your book, chapter 15, plus the log of the concentration of the conjugate base divided by the concentration of the acid. And so it's pretty useful. A pretty useful equation. It can save you a little time from the ice charts, but the ice charts will get you to the same answer, so that's kind of a comforting thing to be able to take two strategies and solve a problem. pKa is kind of like pH. pKa is the negative log of the Ka, so it's pretty easy to solve for that as well. Oh, there's the name. Henderson-Hasselbalch. There, hopefully I was close on that equation. And there it is. pH equals pKa plus a log conjugate base over acid. You want to write that down. That's important. All right. What's the pH of a solution containing 0.3 molar HCOOH and 0.52 molar HCOOK? And so this is a great example of one where we have a concentration of a weak acid, which we know will ionize to give a conjugate base, and then we have a different concentration of a salt. This will break into K+, which won't affect our pH, and HCOO minus ions, which of course will be on the other side of the equation. So we're mixing a weak acid, and we're mixing its conjugate base. So we write the acid equation out. We say, okay, this is our acid. It's going to give up a hydrogen, because that's kind of what acids do, and it's going to leave this ion here, the HCOO minus. Then we set up our ice chart. and we say, okay, we start with 0.3 of HCOH. We start with no hydrogen that we know of, and we actually start with 0.52 HCOO minus, because this will break into 0.52 molar HCOO minus, 0.52 molar K plus. And so it's a little different than the old ice charts we've done, because we don't start with just acid 0, 0 and work from there. We start with acid and some of the conjugate base already present from the salt. And so then we do set it up like our normal ice chart, where we lose an amount in our reactants and we gain that amount in our products. And then we set it up for equilibrium, 0.3 minus x, 0.52 plus x. And this is an example of the common ion effect. So here you could look up Ka. They're going to say that because our acid's very weak, we can assume that 0.30 minus x is approximately equal to 0.30. You could certainly do that solving for the whether or not it's greater or less than 5% of the original concentration, which I can show you in class. It's a super quick job, easy to do. But they're going to say that it's okay to use the approximation, so they're dropping the minus x plus x from these, saying that that change is minimal, and we can just solve for hydrogen ions, basically. And so once they have those, they're going to take a couple shortcuts here. They're going to go straight to Henderson-Hasselbalch, which is fine. And they're going to find the Ka of this acid in the book, and they're going to take the negative log of that to get the pKa. And once they've done that, they can solve. Here, our end goal, of course, is pH. So they've got a pKa, they've got a concentration of our conjugate base, they've got a concentration of our acid, and so they plug those values in. It looks like this, and you end up getting a pH of 4. If you were to use these, pardon me, and actually set up like we did before with the K from the book is equal to products over reactants, and solve for your x squared and do the whole quadratic formula, it's going to take you a couple extra minutes. You're still going to get the same answer. So however you're comfortable solving, it's the way you should solve it. So let's look at buffers. Buffer solution is a weak acid or a weak base, and the salt of that weak acid or that weak base. But you got to have both. You have to have both because a buffer has to be able to, if you add acid, it has to be able to take that excess acid and neutralize it. And if you add base, it has to take that excess base and neutralize it. So having that weak acid, weak base back and forth is really what makes a buffer solution a buffer solution. So a buffer solution resists change in pH when you add small amounts of either an acid or a base. So if we have an equal mixture, this is one you're going to see a lot, acetic acid, and then the salt with the sodium on the end of the acetate ion, then what you get is if you add a strong acid, then our conjugate base can accept that hydrogen and just make more acetic acid. If you add a strong base, then our acetic acid end can donate hydrogens, and we can make some acetate ions and water. And so we're kind of in a place where we can do a pretty good job of neutralizing either situation because of our weak acid, weak base salt mixture. And that's what makes a buffer a buffer. So here's the difference, of course. If you add hydrochloric acid to just plain old water, the pH is going to drop super, super, super fast because it's going to make it very acidic very quickly. If you add pH to a solution that is a buffer made of, acetic acid, then you'll change your pH a little, but it takes a lot of molarity. It takes a lot of moles of hydrochloric acid to change that solution because the buffered solution, you keep adding hydrochloric acid and it keeps neutralizing it with the acetate ion. And so buffers are a little better at resisting pH change, and that's really about all they do. And don't get me wrong, they're very important. Not trying to knock on buffers. They're super important. You and I are alive because of buffers, which is great. So you can answer a question like this: which of the following are buffer systems? We got potassium fluoride and hydrofluoric acid and potassium bromide and hydrogen bromide and all of these different things. And basically you just have to ask yourself, well, is it a weak acid and a weak base? If it's not, then it's not really a buffer. KF is a weak acid, and the fluoride ion is a conjugate base. So that's going to work fine as a buffer. HBr is a strong acid, so that's not going to be so good. CO3 2- is a weak base. HCO3 is a conjugate acid. That'll work just fine. And so you just have to look at, what's my salt and what's my acid. If my acid's strong, it's a no-go. If my acid's weak, or a weak base, and we should be just fine. So now we can do a problem with this. What's the pH if we have 0.3 molar of ammonia and 0.36 molar of ammonium chloride buffer system? And then what's the pH if we add 20 milliliters of 0.05 molar sodium hydroxide to 80 milliliters of the buffer solution? I think this is one of the reasons that the chem test is so hard is there's just so much information you don't know where to start. Let's start right here. Just do the first part. pH of a buffer solution. Okay, we know NH3 is going to be 0.3. We know NH4 is going to be 0.36. Chlorine minus is going to be 0.36, but it's not that important because it doesn't change our pH. So let's set it up for an acid. NH4 goes to hydrogens and NH3. And then we can set up our Henderson-Hasselbalch equation. We can find a Ka from the book for NH4. And we can take the negative log of that to get a pKa. Then we can solve for pH, 9.5 plus log. The 0.3 is our ammonia right here. This is a conjugate base. And then our 0.36 is the ammonium, which is our acid. Over here, if you did an ice chart with Ka, you'd still get the same pH. You solve it however you're comfortable solving it, as long as you get the right answer. So they do 9.17 doing Henderson-Hasselbalch, which is fine. Alright, so now we have to look at this. We're adding 20 milliliters, 0.05 molar sodium hydroxide to this. So you say, okay, we're adding sodium hydroxide. Sodium doesn't affect it, but the OH minus does. And so let's start with moles, and we're going to end with moles. So we have a 0.029 moles to start with, 0.001 moles of our hydroxide, because if you have molarity and a volume, molarity equals moles per liter. That's the way they're getting these here. Oh, pardon me. And you have 0.024 for your NH3. So when we end, we're at 0.028. We're ending at 0 of the hydroxide because the ammonia has to kind of absorb that hydroxide. And we're going to be making more NH3 as a result of that. So then you look at your final volume and you say, well, we've got 80 milliliters and we've added 20 milliliters. So we're ending up at 100 milliliters. And so our ammonia would be 0.028 moles divided by 0.1 liters. And that would give you your concentration there. And your NH3 is your 0.025 moles and your 0.1 liters. And that would give you a concentration for ammonia as well. And then you could solve for pH using those values right there. And so that's the way you can solve that problem. Now they didn't quite have enough space, I don't think, on one PowerPoint slide to really show you how you take volume and molarity and then calculate the change in sodium hydroxide. So I can sure show you that in class to kind of give you an example of that, because it's a little tough to just start and end with these values without showing you how they kind of calculate it to get those. But I can sure show you how to do that. So when it's all said and done, our pH is 9.2. So it didn't really change much. You added 20 milliliters of sodium hydroxide, and the pH barely changed. And that's because it's a buffer. But it did go up to become a little more basic, which is what it should be doing if we're adding sodium hydroxide. So there's always an opportunity to kind of check our logic there at the end, which is nice. Alrighty, so here's the application for buffer systems in biology, which is great for me because I'm primarily a biology teacher. But here you go. The red blood cells in the capillary. Capillary is a super small tube. Red blood cells kind of flowing through here. And the red blood cell, the erythrocyte, has the ability to act as a buffer, and that's super important because you can see here carbon dioxide from, cells in your body going into the red blood cell and mixing with water, and it's making this carbonic acid. And the pH of human blood's like 7.4, and the pH of human blood that we can stay alive at is really, really super crazy narrow. Our body's incredibly picky with its pH. And because we have this really cool like carbonic acid and bicarbonate equilibrium existing in our blood, we have a great buffer system right in our red blood cells, so that if we have a little too much acid, we can neutralize that. A little too much base, we can neutralize that. And so here you have, a weak acid and its conjugate base, and that's like the definition of a buffer system. And so it's just super cool that God designed us to have this, because it allows me to do things like drink super acidic coffee for 10 hours a day and not die because my blood is too acidic. So super thankful for that neat little trick. Then here we have pretty much the same red blood cell diagram in reverse. Here the bicarbonate's going in, and we can absorb hydrogen ions and release the as CO2 in the lungs, which is really cool. And then that keeps us pretty neutral. So reversible reactions, you gotta love them. Cool. So that takes us to titrations, and that's actually where we're going to stop for this recording. So we'll practice some more in class with ice problems and Henderson-Hasselbalch, and hopefully we'll get familiar with adding acids and bases to buffered solutions, because it is tricky, but it's doable. So thanks for your time. I hope this made a little bit of sense, and we'll keep working through it together. So thank you.